Hello, my dear students, and welcome to our last lecture with this electronic measurements and instrumentation course. Our long 12 weeks have now reached an end, and we are now in our final stage with our digital to analog converters, or what we can call, or what we can abbreviate it as DACs. In the previous two lectures, we have go into the concepts, the system level, as well as the electronic circuit level for digital to analog, for analog to digital converters. And we have studied together different types of ADCs, and also we go into different circuit schematics for various blocks in ADCs. Mainly, we give focus to sample and hold and comparators. Today, we are into a reverse process, which is actually a part of the initial process. I mean, the DAX is a part of the ADC's log diagram. So let's see together how we are going to demonstrate DAX. Okay, so let's go into DAX. As usual, we start with referring to our textbook by Electronics Instrumentation and Measurements by Bell, where you can refer to chapter 5 for DAX. And still you have also additional extra resources, online resources that you can find on our e-learning page. So let's go to what is inside a digital to analog converter. So simply, the simplest way to observe a DAC is to monitor the process of a DAC as a reverse process for the ADCs. If you remember, when we first studied the ADCs 2 chapters ago, we introduced what we can call the transfer function of an ADC, which correlates the analog input for an ADC to the digital output. So the simplest to start, I think, for a DAX is to consider a reverse process. So instead of having an analog input for DAX, we have a digital input that vary based on the number of bits used. So for example, what you are observing now is a 3-bit DAC. That's why we have an 8 states for the digital input signal. And we have an analog output y-axis. So it, in a very simple manner, this is the reverse characteristics with respect to the ADC. And again, if you remember in the ADC lecture, we have already highlighted the difference between what we call a unipolar and a bipolar ADC. So using the same terminology, we can still define a unipolar and a bipolar DAC, where the unipolar DAC is with an expected full scale range in one direction. So it's from 0 to full scale range, while in the bipolar, you are expecting an output analog voltage that vary from negative full scale to positive full scale. But here maybe we have more detailed description when we consider a bipolar representation. So we have 2 types of bipolar representation. So of course, the unipolar is still the same definition, where we have a variation between 0 to full scale minus 1. Which should corresponds to 3 ones, for example, when you have a 3-bit DAC as an input, I mean, and the output will be full scale range minus 1. And for minus 3 significant bit, I mean, not minus 1. But for the bipolar, where you can find it in the mid graph, there is 2 types. So we can have a standard bipolar with a variation between negative full scale to positive full scale minus LSB, or we can have what we can call a sign magnitude bipolar. So simply, the sign magnitude bipolar is a way to represent the sign in the most significant bit, what as you can see here. So when the most significant bit is 0, that means that the output is positive, while when the most significant bit is 1, that represents that the output is negative. This is a simple way where you can represent your, or you can use a bit to represent the sign of your output. These are different types of transfer characteristics for DAX. Generally, we can have this block diagram as a generic block diagram for DAX. The main idea beyond the DAC, which we are going to demonstrate in a more detailed manner later on, is that each input bit in your DAC represent a certain weight to be converted into analog signal. This weight depends on the position of the bit. So the minimum weight is for the least significant bit, and the maximum weight is for the most significant bit. And this weight is controlled based on a ratio related to the number of bits, as you can see here. So, for example, if I need to write an equation that represents the output analog voltage for a 3-bit amplifier, sorry, a 3-bit analog to digital to analog converter, I can write V output equals VR times. So the most significant bit, which I call it P1, will be weighted by 1 over 2 to the power 1, which is half. This. The second bit, which is the middle bit in the case of a 3-bit DAC, which we call it B2, is weighted to 1 to the power 2 to the power 2. So 1 to the power 1 to 1 over 4. And finally, the third bit, which is definitely the least significant bit in this case, which is, we call it P3, will be multiplied by 1 to the power 2 to the power 3, which is 1 to the 8 to the 1 over 8. And then we close the plug. Of course, as usual, please accept my apologies for a very bad handwriting. So simply, based on the position of these P1, B2, and B3, I mean, they are 1 or zeros. Definitely, these are the 2 states possible for these 3 bits. So based on these 3 states, you can determine the output. So simply, if the input is 3 zeros, that means that you are multiplying VR times 0, and then output will be 0. If it's 3 ones, then you're going to have half plus 1 over 8 plus 1 over 4. 1 over 8 plus 1 over 4 plus half. Then we have the output of our case. So simply, if you have here, so this will ends up to 2 over 8 plus 1 over 8, which is 2 over 8, yes, plus 1 over 8, which is 3 over 8. And then this, we can make it as 4 over 8. So the output will be 7 over 8, which of VR, which is the full scale minus least significant bit. If you have 0, 0, 1, I mean, that's only the least significant bit is only 1. So the output VR over 8 and so on. So you can make this transformation function. And simply, what we are going to do now is to check how we can transfer this transfer function, this mathematical transfer function, how we can transfer it into an electronic circuit. And in order to do that, we simply have, of course, there is more than 2 types, but in a basic understanding, you can say that we have 2 famous types for DACs. The first, what we call a binary weighted resistor, or BWR DACs. The idea of a binary weighted resistor actually is already known idea since when you were in year 1. If you remember the very famous circuit you studied in electronics when you study the operational amplifier, and when you study the concept of the weighted summer or the weighted adder, when simply you grounded the non-inverting input of the operational amplifier, and you use this resistance with respect to the feedback resistance in order to give different weights for different inputs. Herein we have a common input, which is VR, and you vary the input, or you vary the weights based on a ratio here. So the first one will be R over 2R, which is half. The second will be R over 4R, which is 1 over 4, and so on. So you simply control this with the weighting factor, as you can see here. and you enable this branch or not based on the state of the binary state. So if the most significant bit is high, then you have this as a short circuit. If it's low, this is an open circuit, and so on. So simply, it's you are controlling here with an on-off switch. And already we have studied this concept in the previous lecture when we study the concept of the sample and hold, and you can use you can know that you can simply use a MOSFET as a switch for this case. So simply, if you enable a MOSFET here, and this is the gate of the MOSFET, if you have a high signal, the drain and source are connected, while if you have a low signal, the drain and source are not connected. So you can simply use a MOSFET for this purpose to act as a switch. So in this direction, you have a weighted function, which is typically the same as the transfer function needed for a DAC. So you simply implement a very simple DAC or digital to analog converter using a weighted sum. But maybe there is a main drawback related to this topology. That's in this topology, you have to downgrade this resistance based on the number of bits. So as you can see here, we have 2R, 4R, 8R. Then we reach 2 to the power NR. So for example, if you have 8 bits, then this will be into 128 R with respect to R. So if this 1 kilo ohm, hypothetically, this should be 128 kilo ohm, and so on. This huge dynamic range in resistance. So you are using in the same system, in a same circuit, a variation of 128 or 256 and so on, very range of resistance, with of course the problems that related to the tolerance of resistance. So you are not using identically the same resistance, so there might be some sort of a shift between these two resistance. That makes some sort of a challenges for this design. So of course this design is hypothetically functionalized as needed to perform as a DAC or digital to analog converter, but whenever it comes to implementation, you might face problems related to the big variation in the values of the resistors. That's why we go to the second type, which is still the same concept, but with slightly different implementation, which we call it R2R ladder DAC. The R2R ladder DACs is still using the same concept of a weighted function. So the concept is the same. But what we did here that is, so instead of having this weighted function coming mainly from these resistance, we make a different way. So we have here an R resistance that is connected between each two branches. So if the voltage here is VR, the voltage here will be VR over 2 and so on. So that, and you keep all these series resistance R with the same value to R. So as you can see here, the only two values you use in this circuit is R and 2R. That's all. So you need only two values of resistance instead of a huge amount of values, or with different, or with a big variation, where we use in the case of the first structure when we use the binary weighted resistance topology. So here we are only using two types of two values of resistance, R and 2R. But the question is how we make it that if this VR, how comes that this will be VR over 2, and how comes that this will be VR over 4, and so on? How we can consider this? This is a very simple way. So let me try to explain it in a white slide, and let me use the annotation again. So I will assume a very simple example that we have only 2 bits. So if we have only 2 bits, we can say that we have something like that. So this is negative, and this is positive. And we connect this to the ground as usual. And here we have the first branch. And also we have the second branch. And these two branches are connected with a resistance. And this is the input voltage. So the values here, this is 2R. And this is 2R. And this is R. And based on that, we also have a resistance here to the ground with a value 2R. So I think I have here. Yes. Okay, and let's print. So this is the value is 2R. Okay, very simple. So this voltage, input voltage is VR. So we don't have a problem with that. This is the input voltage. And definitely based on what we already know, of course, we have here a feedback resistor with a value R. So of course, we know that this is a virtual ground because this is positive, and for an ideal operational amplifier, V positive equals V negative. So this is a virtual ground. Okay, great. So this is VR. This voltage equals VR. And here you have a resistance R, and then you have two parallel resistance, each of a value to R. Why these two resistances are parallel? Because simply this is a common node. This is a virtual ground, and this is a ground. So this is practically the same node. So these 2R and 2R is parallel. So 2R in parallel will equivalent to R, value R. So when this is a voltage is VR, and we have a resistance R and R, and this is connected to the ground, then the voltage here is a potential divider, which is simply VR over 2. So in a very simple manner, when we use this laddered R to R configuration, each time you go directly to the next branch, the voltage is divided by 2. That's why if you return back to this configuration, when I say that the voltage here is VR, the voltage here will be VR over 2. The voltage here will be VR over 4, and so on. So while you are going from left to right, the voltage is divided by 2 in each time you pass this horizontal resistance R. And that's lead up that here the voltage is VR over 2, and we have also another ratio of 2 between R and 2R. So the weight of this branch in general will be VR over 4. Again here, the voltage reaching this point is VR over 4, and you have a ratio R to 2R. So the voltage reaching here will be VR over 8, and so on. So you reach the same equation with a weighted equation, but with only using two values of resistance, R and 2R. So this is simply the main advantage of the R2R ladder DACs with respect to the weighted DACs. Coming to some important parameters related to the DACs, which is already also discussed for the ADCs as well. One of these parameters is the resolution, which is representing to the minimum voltage variation that can be outputted from our DAC. So usually the resolution, as you know already, is a concrete function of the number of bits. So usually we consider the resolution in the terms 2 to the power n. So when you have 3 bits ADCs and you have 8 states, this is your resolution. The higher the number of bits, the higher the number of states or the resolution. And in order to calculate it in terms of voltages, it's very easy. So it's simply the full scale range over to the power n. So we already discussed this before in our ADC lecture. So if you have a full scale range of 1 volt and you are using 3 bits, that means that the minimum variation, the minimum analog variations that you can observe is simply 1 over 2 to the power 3 or 1 to the power 8 voltage. So when the least significant bit change, when you change from 000 to 001, the analog output voltage will change from 0 to 1 over 8 voltage. So this is the minimum observable variation. And this leads to what we call the accuracy of our DAC. Again, the accuracy of the DAC is generated from the accuracy of the ADC. If you remember, we already mentioned that while we are discussing the quantization process in the ADC, is that the quantization process is a quantization error, is not a reversible error. What I mean by is not a reversible error is simply that if the initial analog voltage is 2.6, okay, so I will automatically correlate this voltage to the state of 2.5, which is, for example, 110. Okay, so now there is an error between 2.6 and 2.5, which is 0.1. And I'm converted into 110. When the DAC receive this 110, it will convert it back into 2.5, not 2.6. So I didn't reserve back the 0.1 error. So this is simply the accuracy. And by nature, the accuracy is plus minus half less significant bits. So for example, referring to the example I just mentioned with 1 voltage full scale range and 3 bits representation. So the minimum least significant bit variation is 1/8 voltage. So the error will be plus minus 1/16 voltage. This is the accuracy for our DAC system. So accuracy is an important parameter to be discussed for DACs. Also, what we call the conversion time, which is simply the time needed or number of clocks from starting the analog input voltage up to getting from starting the digital voltage up to getting the analog settled steady state analog voltage. So this is what we call the conversion time. And definitely this is very, very critical for real-time high-speed application when you have a series of data coming from the DAC and needed to be converted into analog voltage. Of course, settling time is very important for system on a chip, for sensor on a chip, with sensors with relatively high data rates. You have to consider the conversion time. And finally, of course, for any electronic circuit, you have to consider the stability, which is simply the performance of your circuit under different environmental conditions. Like, for example, when the temperature is relatively high, the humidity, the linearity errors, and the gain of the amplifiers, and all these stuff, how you are measuring, of course, the frequency, which is, of course, the frequency response of your system, which is also another critical point. This is a very simple overview on what we call the digital to analog converters, or DAC. Again, this represents the final stage of our course related to electronic measurements and instrumentation. Thank you very much for your concentration. I hope that these series of lectures were considered as an added value for you, and looking forward for a new course together. Thank you very much, and see you later on.